I'm going to present today is Fog Hive Remake, which is the focus of my PhD project, supervised by Dr. Christian Schau. I only started the project in December 2013, and as you could make out from this photograph is that it's based on water, which is one of the problems which was identified by many of the speakers today. And water is actually one of the major global challenges that we face today, and it's only going to increase with time. As we know, most of you probably know, only 0.8% of the water available on Earth is fresh water which we can use and which we have access to. And at the same time, our water footprint is increasing. Every year we use more and more water, and also it's not evenly distributed, which is a major problem for some nations. As you can see, in the Western world, it has been estimated by Fred Pearce that we use approximately 370 liters of water per day, while in water hotspots, which are marked with the pale blue, people survive from distant water sources which are non-treated, polluted, from only 7 liters per person per day, which is of course quite shocking and leads to many health problems. And how that will develop in the future: in 2030, the Organization of Economic Cooperation and Development have estimated that nearly half, or 47% of the world, will actually live in one of these water-stressed regions. So it is a very important question. And even in the most harsh of conditions, certain species have adapted to survive. Since this is an ecological conference, I thought these would be quite appropriate examples. The first image that you see here is an air plant, or one of the bromeliad plants, or from the Tillandsia family. They survive in the desert through tiny hairs. As you can see, they don't really look green, they look pale or white. That's because they're all covered with tiny hairs on which moisture from the air gets caught, and then because of the angle of the leaves, gets trapped inside the plant, so the plant can survive with very minimum water. A similar strategy is adapted by the Pinus canariensis, or just the pine which is found on the Canary Islands. On it, the pine forms a very dense network of needles, and when the fog on the Canary Islands passes through, it forms larger drops, which then start dripping from the plant, and the plant can absorb it to sustain its life. And what's interesting about that is actually the drops fall down, and so they sustain the lower plant life as well, which develops the entire forest ecosystem. And of course, when we think of the desert, we think of cacti, which because of their very waxy surface, very hydrophobic surface, manage to capture water, suck it into their bodies, and then they're protected by these needles, which of course also act to get water from the air. And people have actually studied fog collection potential ever since the 1950s. This is a map showing all the projects which have been measured. So there might be more potential, it just hasn't been scientifically proven yet. As you can see, it spreads around across 6 continents. And these projects are all at different stages. Some of the most successful ones have actually been in Yemen and Oman, which are also one of the major water hotspots where people need most water. But there were also water conflicts there. There was a war over water. And also in Chile and the Canary Islands, where you get fog oases. Now, fog oasis is a phenomenon. I've chosen 2 projects here. It's a very quick case study. The one you see here is in Chile, near Falda Verde, where you have very dense clouds coming from the sea, which is advection fog. That's an almost constant fog belt. While in the Canary Islands, we have something which is more seasonal. There, the pine trees survive thanks to the additional water, which is provided from the fog in the driest seasons. And what we're trying to do is test fog collectors in Scotland. So we're trying to find places where similar fog conditions can be found. So we're studying lochs and bends or peaks, which you can see here, a bit more detailed. And so the project in Powder Verde, Chile, was used to provide water for agriculture for the local population, because when there's no water, you can't grow food. While the project in Spain was used to reforest a degraded forest area by pine and local oak species. And as you can see, in both those locations, the fog was present at the very tall peaks. But what we noticed in Scotland, at least from photographs, is that fog can be present at the lower, by the water source in the form of mist, or when the mountain actually breaks the cloud cover. And so what we want to test are these innovative 3D fog collectors, which have a very stable hexagonal design. And on the left, you can see the conventional planar fog collector, which is deployed by a charity called FogQuest. And it's quite large. It measures 4 by 12 meters. And the problem with it is that it's very prone to, it is efficient because it's been employed, but it's very prone to damage from wind, because whenever there's wind, you also get, there's fog, you also get a lot of wind. Also birds destroyed, people. It's difficult to maintain just because of its size, difficult to put up. And another one which was used in Spain is the cylindrical. Now that's quite small actually, that's only got a 46 centimeters diameter. And it's mainly used just to measure the efficiency of the fog. And it also operates on a different system. It has vertical strings, while the conventional has a mesh that's used for agriculture. And so this is one of the locations that we want to test the 3D fog collector, the polyhedron one. We've identified Ben Nevis, one of the most probable locations, just because it's got a constant fog belt, and it's also got a very good forecast on the cloud cover, which you can see here. It's got a webcam, so we can see live how the visibility changes, and therefore how much fog there is. The problem is, of course, there's not really a need for water in Scotland, but the idea is that we're gonna test these structures, optimize them, and then once we get to a more advanced prototype, we could get funding through Horizon 2020 or some other major program to go and help people in where they need water, in Chile, let's say. And these are the different configurations that we want to test. Triangle, a square, a hexagon, and an octagon, to see which one we could take to the next stage, which would be a more advanced prototype. And we're planning on doing a very simple 1 meter by 1 meter square modular system, arrange it in different geometric configurations, and measure using quite simple metal plate and quite simple connectors, and just measure the fog water which is collected. What is very important for the project is that we optimize the structures for what we call SEPIA, which is sustainability, efficiency, passive, innovation, and affordability, so that the projects are not very expensive to run, but they also contribute to the environment in terms of their materiality. We've studied a lot of different mesh types. We're also looking at using, at least at the mock-up stage, very simple connectors, which are used just to make agricultural plots, and just making the system really as easy to construct and maintain as possible. And we do have some specific innovations kind of already settled. We are cooperating with the Institute of Textile Technology and Process Engineering in Deckendorf, Germany, who have supplied us with this quite fascinating material. I don't know if you can see how 3D it actually is, but it's actually like a sponge, and it mimics quite well what the tree homes or what the needles on the pine trees would do. And it's quite obvious how much more complex it is when you compare it to the conventional rational mesh, which is the agricultural mesh which you use for potato sacks as well. So I guess you've all seen that. And what's also interesting to us is to measure whether by employing just a paler color, the fabric would be cooler, and then it would contain some water, so it'd be more efficient, because conventionally they only use dark colored meshes. And so this is, the project's called Folk Hive Remake, because there was already a folk hive developed by Dr. Christian Schau in this, via these ideas. It would be quite easy to assemble, and Folk Hive Remake would be even easier because it would be even more modular, but it would only take a couple of minutes, a couple of people, one day, and a van to assemble the whole structure until it's functioning and starts contributing to the environment and to the people in different ways. These are some calculations based on previous projects. So from one hexagonal unit, which can be easily scaled up to 6 meters by 6 meters side, instead of the 1 meter by 1 meter, we could have, let's say, water for 66 people per day, or we could irrigate 290 meters square of maize, which would provide a lot of food, or we could use it for reforestation via the aloe vera plants, the Tillandsia air plants, which grow naturally in the desert, so they would have a very good survival rate. And that is quite key for our ecological and hydrological restoration strategy. As you can, folk collectors are usually employed at the highest locations possible, so you have different elevations. And this is a new concept because previous designs only used to irrigate one specific type of plant or a specific tree, while we see the ecosystem as one combined whole. So the ecology and the hydrology are joined, and what we want to do is irrigate these local species like the Pinus carnariensis until they grow and they're self-sufficient, so that the ecosystem can work on its own. And then the water, after it's collected by the folk collector, stored, distributed to the higher altitude. It would go down to the lower altitudes, to the sand dunes, where it would also provide nesting grounds for birds. Then it would go down to the water source, and then go back up again to the folk collector. And so it's a continuous cycle. And so that it's not just in graphs. This is another interesting idea. This is what the desert looks like at the very rare events of desert bloom. So when little rain does occur, all these species of flowers start to bloom. And this is one example of the Valena Valley in the Atacama, which happened a couple of years ago. After a bit of rain, all the flowers created this beautiful array of colors in the desert. And we're thinking of using these specific species, which is the Radifolia ficularis, to create something like this. So the top image is what was the previous folk hive project, and the bottom one is what can be created in the Atacama just by employing local species, especially perennial ones, which are seasonal, just to create a balanced ecosystem, which would also attract visitors and contribute to the world. If that's too strong of an argument. And so and as a conclusion, there's a video in case you're interested to see anything further. Thank you.